Great. Thank you very much to the organizers for giving me the opportunity to give this presentation here today and speak to this audience. And also I'd like to just start by acknowledging a really large number of co-authors who participated in the three studies in the Uinta Basin, Utah that I'm going to describe in this talk. So it was really a large body of experimental and modeling work. In particular, I need to highlight the contributions of two people pictured in the lower corner there, Pete Edwards, who did the modeling work that I'm going to discuss here, as well as Jim Roberts, who really led these studies through 3 different winters in a remote part of Utah. So I want to start just by contrasting what we're interested in here, which is the oil and gas ozone problem, with what we think we know pretty well, what we do know very well with regards to the urban ozone problem. And that's nicely illustrated if you just look at the seasonality of ozone. In this case, I'm showing you year 2013 in the Los Angeles Basin, choosing Riverside, California as a canonical receptor site in that area. And the picture you see here is what you expect, that is to say the ozone peaks in the summertime. And we know that over the course of the past 40 years, as urban emissions have come down, the ozone problem has also been substantially mitigated, if not completely solved. But what we know from our more recent experience is that this contrasts quite considerably with oil and gas ozone that peaks very strongly in the wintertime, and which is a problem that's only really been recognized to occur within the last 5 or 10 years. And the question I want to ask here is, how do these problems, which have these very different seasonalities, appear from an atmospheric chemical standpoint, and what is the atmospheric chemistry that underlies these, and how does an atmospheric chemical understanding allow for development of mitigation strategies in these 2 very different cases? So to do that, we went to the remote area of northeast Utah that was just described in the last presentation. This is an expanded view of the Uinta Basin showing oil and gas wells, which number about 10,000 in that area. We went there in 2012, as Ravon just described, in a year when there was very little snow on the ground, and went back again in 2013 in a year that was much more normal meteorologically in terms of snowfall and snow cover. And I'm going to spend a lot of time just contrasting what we saw in those 2 different years to try to get at an understanding of response of ozone in the wintertime to NOx and VOC emissions. I will say that we were also there in 2014. That was a year which was very much intermediate between the snow-free and the snow-covered years, as you can see from this picture. And I would direct you to an analysis by Patrick Verres for some understanding of what we learned about radical sources in that year that informed the contrast between the 2012 and 2013 years. So this is a summary of ozone across those 3 years. You've seen some of this already from Ravon's talk. We went and spent 6 weeks in Utah in 2012 looking for ozone, and found that although we had a very clear diurnal cycle in ozone and very clear photochemistry, none of the measured ozone was anywhere near the National Ambient Air Quality Study that's shown by the dashed line in the figure. So as a result, we went back in 2013 and found multiple ozone events very consistently above that standard during the snow-covered year, and you can see that, as I mentioned before, 2014 was very much in between those 2 years. So the approach to trying to understand the NOx VOC sensitivities of what we just seen is going to be a box model. And this is based on the master chemical mechanism, or MCM. The particular variant of that model that was brought to us and developed at our laboratory by Pete Edwards is called DISMAC, whose acronym is spelled out right here, and I won't read that to you. But the basic idea here is that a box is a very appropriate approach to use in a place like Uinta, where the air is very confined within that mountain basin. We'll put primary emissions into that box of NOx and VOCs, and we'll tune those primary emissions to match the total loadings of VOCs and reactive nitrogen, rather than tying that to any given emissions inventory. And that's what's going to allow us to really get at the sensitivities to those emissions. There's a physical loss term out of the box that's constrained by what we see for the diurnal variation of stable compounds within the basin. And then the real strength of this model is that it has a very detailed chemical scheme. So we're going to apply something like 13,000 chemical reactions to generate photochemical oxidation products from these primary inputs, to see how well we can reproduce those photochemical oxidation products and what we can say about the sensitivities to primary emissions. And I will say that for 2012, we're doing something a little different than we do in 2013. Because 2012 was a very regular pattern day after day, we can run that model forward to a steady state and compare it to a diurnal average of the model. Whereas in 2013, there's no real obvious steady state in the observations, so we'll look at a single period or buildup event. So to start with 2012 and figure out what we learned in a year when the ozone did not exceed the standard, you can see the diurnal average ozone is this black trace on the upper graph. And we can reproduce that actually reasonably well with a model which is shown as the blue trace. And the difference here, the late day difference here is entirely due to how we're dealing with our dilution scheme. The interesting thing about this model to measurement comparison is the radical sources that go into it. And I'll describe on the next slide exactly why those radical sources are so important to understanding NOx and VOC sensitivities here. But the key is that we normally think of the photolysis of ozone and its subsequent reaction of water vapor as the largest source or the most important source of net radicals into this system. And in a wintertime environment, of course, that's a very small source. And indeed, in this case, it's only about 9% of the total radical input. There are other radical sources that are derived from heterogeneous reactions of nitrogen oxide species. I can't go into very much detail in this talk here, but those are things like nitrous acid or HONO and ClNO2. And then there are radical sources that are derived, as part of the VOC oxidation scheme itself, carbonyl compounds, right? And what you can see is that's really the majority of the radical source in this case. And without the model being forced to produce these the majority of these radicals through these different kinds of schemes, you actually don't get any ozone out of the simulation. So to go a little bit further with that and understand why understanding those radicals is important to the NOx VOC sensitivity, this is the mean VOC from 2012 and the mean NOx from 2012. So the NOx levels there are characteristic of what you might expect from an urban area. VOCs, on the other hand, are much, much larger than what you would typically expect to see in an urban area, an average of about 230 parts per billion. So to look at this, you would think this system might be in a situation where it was sensitive to NOx and fully saturated in VOCs just because there's so much more VOC than NOx. To really understand that, you have to think about the way radicals behave in the wintertime and compare the production rate of radicals that I showed you on that last slide, we'll represent that as Q, to the loss of those radicals to NOx, because one of the roles of NOx is to pull radicals out of the system in addition to making ozone. And so NOx-limited systems can be defined as whether radical production is large relative to loss to NOx or small. And if we look at the data for the 2012 study, what we find is that actually, in relation to this metric, it's very heavily in the VOC-limited regime, right? So even though you have a lot of VOCs and moderate NOx, you end up in a situation that's very NOx-saturated and very VOC-sensitive. And that's normal. That's absolutely what you expect to see in the wintertime because this term Q is always going to be small for most environments in the wintertime. So far so good. We got what we expected. Now let's go to the rather unexpected or only recently recognized as important problem of winter ozone in these oil and gas regions. So here's 2013 when the snow is on the ground. I'll just say, as others have already said, the effective snow cover here is twofold. One is you get increased photolysis rates because of reflection off the snow. And two, a dramatic reduction in the boundary layer height, essentially making that box much smaller, and that's concentrating everything that's being emitted at the surface into a much smaller box, right? So we're just going to simulate this 6-day period, not running to steady state, and see what the model does. But first, I will tell you what the comparison between NOx and VOCs is between the 2 years, okay? So because of that dramatically lower boundary layer, we see that in 2013, VOCs were approximately 3 times larger than they were in 2012, okay? So that's a very large effect. Interestingly enough, if you look at the NOx between the 2 years, there's very little change. I'm not showing you total reactive nitrogen here, and if you look at total reactive nitrogen, you'll see that between the 2 years that did scale approximately the same way the VOCs did, but because of the increased photochemistry, you end up with more aged NOx essentially, and you have about the same level of NOx between the 2 years, which is already an interesting observation. In other words, the amount of the increase in the ozone is in some ways almost proportional to the increase that we see in the VOCs between the 2 years. So moving forward to the model, you can see that over that 6-day period, the observations of ozone are shown in red, the model is shown in blue, and Pete's model can very nicely reproduce the buildup of ozone over a single event like that. And it doesn't just reproduce ozone alone. It also reproduces a lot of different photochemical products, such as peroxyacetyl nitrates and acetaldehyde, all to within 1 to 4% in an average sense. So we're doing well with the model in terms of predicting the ozone. In order to understand the NOx VOC sensitivities here, we're going to appeal to what we know about the radicals that are driving this process. So if we just look at the graph on the left here, these are the radicals that are driving that ozone production in 2013. And we'll note that there's almost 19 parts per billion per day of radical generation in this case. The case that I showed you for 2012 was less than 3 parts per billion per day of radical generation. In this case, our conventional or canonical radical source from ozone photolysis is only about 4% of the total, so a very small contribution. We get some contribution from these heterogeneous reactions of nitrogen oxide species, but again, that's only about 10% of the total. It's not the major contributor. The big contributor here are these 2 pieces of the pie, which are going to be almost exclusively from the photolysis of aldehyde species that are themselves derived from these intermediate steps in the VOC oxidation scheme for the most part, with a little bit of extra formaldehyde added as an emission in this case to make the measurements of formaldehyde agree with what the model predicts. So what does that do to NOx VOC sensitivities? So what Pete then did is take the base case model, shown here as the red point, and then vary the emissions into that box of both VOCs and NOx to construct an Ekman diagram or an ozone isopleth for this system. If you just take cuts across this diagram, either horizontal or vertical, you can pull those out and show the NOx and VOC sensitivities explicitly in the bottom graphs. And what you see is that this very large radical source has actually pulled this system completely out of NOx saturation to the point where it's essentially optimized the ozone producing efficiency of the available NOx in the system. And it's also pushed the VOC sensitivity out a little bit beyond the point where it's VOC sensitive, right on the edge of VOC saturation. Okay, so very different situation with respect to NOx and VOC sensitivities. I think what's instructive or interesting about this is to then make the comparison between the summertime urban ozone problem in terms of what we know about NOx and VOC distributions to these wintertime oil and gas ozone events. So to do that, we can appeal to data that we have from the CalNex campaign in the summer of 2010 in the Los Angeles basin. These measurements are from Pasadena, and compare those to measurements taken in the winter of 2013 in the Uinta Basin. So looking at NOx, if we just look at the distribution of NOx between those 2 basins in those 2 different seasons, we see that there's about 4 times less NOx in the Utah situation than there is in the urban ozone case for Los Angeles. We see that there's about 15 times more VOC than there is in Uinta than there is in Los Angeles. And that's actually by far the most dramatic difference. Of course, these VOCs, as Jessica has already told us, are not the same kinds of VOCs that you get in the urban case. They're largely composed of alkanes that are not very reactive towards OH. So we can transform those VOCs into an OH reactivity space, and when you do that, you get about a 5-time difference between the Uinta Basin and the Los Angeles Basin. But the key here is that if the NOx and VOC levels in Uinta had been the same as what we experienced during summertime ozone in a place like Los Angeles, the system would have been very much in the NOx saturated regime and the VOC, and very, very heavily in the VOC sensitive regime, rather than being very much optimized for ozone production as we see from this model. So, in conclusion, we see now Western oil and gas ozone events are among the most severe ozone events the nation experiences now. The key to understanding the NOx and VOC sensitivities in this system is to understand the underlying radical production. So we actually can do that very nicely from a contrast between 2 different years in Uinta. one in 2012 when we didn't have snow on the ground, and we got what I would say is a very canonical picture for the response of ozone to NOx and VOC emissions in the winter, which is very heavily VOC or NOx saturated, and 2013, where these deeper boundary layers and carbonyl production leads to a situation that's essentially optimized for making ozone in that environment. Thanks.
In order to stay on schedule, if you have questions for Steve, you can ask him after. Thank you.